This is a lens, and this is, we can say, the image plane, and this is focus. So any light coming out from focus goes through the lens, and then you become kind of parallel plane, a plane wave. So you become plane wave, come to here. Okay? So this is focus. Okay? On the other hand, things are going like a parallel to this the central axis, and then it will go through the parallel plane, and then go through here. It is the focus. Okay, so if we have the light source that has a combination of these two, okay, what would it look like? Somewhere is coming from here, and somewhere from here. So from here, as I see, you become parallel plane. So you become like a, as I mentioned, like a zero order, and the other, as I mentioned, coming from at an angle, it will become positive one or negative one order. Okay, so that's the combination of these two. And that's why initially I told you two things. It needs to be collected by the objective lens, projection lens. And second, it needs to have a positive order and negative order to be able to form an image. If you only have a zeroth order, like these, it cannot form image because it's just a plane wave. That's why we usually like it not just become point source. We like it to have a big sigma. Okay. And also the definition for light. What is coherent, incoherent, and partial coherent? Okay. The one that we use in the lithography usually is partial coherent. Okay, so coherent, it is a plane wave, and it's a point source, and we seldom use this one because, as I mentioned, it does not have good resolution. The K1, the minimum is 0.5, and however, incoherent, we don't use it either. Yeah, because as I mentioned, no, it says here, incoherent basically is the light source is infinitely big light source, which is not very practical. Basically, you have the light source much bigger than your objective lens, and it's not very practical. And so it is the incident angle from all angle, positive, negative, yeah, all direction. So it's not practical. So somewhere in between is a partial coherent. Okay, it's a finite. Yeah, as I show here, it's finite. It's not much larger than the objective lens, right? And also is not a point source. It's not zero size. If it is just one point, it's a point source. Is like a coherent light source. So with only certain incident angle. So that's what we always use partial coherent in the illumination. Okay, so here is an example of yeah, I think this one shows wrong. The sigma here is almost 0, and so you can see that you only, if this is objective lens, still you only collect a positive one and negative one order, and each one is this height. And compared to that, if this is partial coherent, the sigma is not 0, then it should look like this. It has a distribution. And as I mentioned, as the P becomes smaller, if this is smaller, this will become bigger, right? And we like, this is objective lens opening. We want the light still be catched by the lens, still catched by the lens. And also, it may also mention, if we have the sigma, then the light not starting from 0, it basically shift to one direction and have a distribution. Yeah. And then also, I just mentioned that second order and above was not collected by the objective lens. And as I mentioned, incoherent, basically, it tells you that the sigma is infinity, much bigger than objective lens. And coherent is point source, sigma is 0. And partial coherent, this is an example, is like these. And a lot of time we have so-called annual illumination, or that one is dipole illumination. They are different. And so-called OAI is an off-axis illumination. So anything still consists of the center, that is not OAI. Yeah. This is still on-axis illumination. Only that this one is excluded, and then it is so-called OAI. Okay, so eliminated on-axis component, then we can achieve like a two-beam imaging. So this one we call it conventional illumination, as I mentioned. But if we kind of take this out, and this, so we start to say this is two-beam imaging, and it is OAI. And for example, here we call it annular. It's a ring type illumination, and this is a quadruple illumination because it has a 4. And if we have only 2, then we call it dipole illumination. So both of these do not have center part. Okay, so that's why we call it OAI. And why is OAI important? Is because OAI will be able to achieve higher resolution. Okay? Let's see. Okay, this is just some example. I cover some good examples of what we'll use in the SML tool. So this we call it conventional illumination. So if you go to choose illumination, and then in here they will ask you to choose conventional or annular, or they ask you to choose quasar or C-quad. We call it C-quad or dipole. And then go in there, they'll ask you to choose. If you choose a conventional, they will ask you to choose sigma. And sigma usually it is from, for example, from 0, could be from 0.5 to 0.96. Okay, so if it is 0.5 means this and that, the ratio is a sigma. Okay, so 0.5 means this only half of the radius. If it is 0.96, so this is almost like as big as objective length. And if it is annular, they will give you sigma in and sigma out. And sigma out need to be bigger than sigma in. Okay? So for example, if I tell you this is 0.83.5, means here the radius is 0.5, the outer is 0.83. Okay. So that's annular means in this one. And if this is a C-quad, if this is quasar, so quasar is usually here, and still they ask you to choose sigma in and out. Okay, so same thing. Here is sigma in, the radius. Here is sigma out. Okay. And then for C-quad, let me put it here. C-quad basically just rotates 45 degrees. So it will be look like this. But ignore this one. It will look like this. But you'll find like there's something missing. Or quasar sigma. What is missing? One component is missing. So then, what's missing? For this one. What's it? What's missing? You have sigma in, sigma out. There's one important feature that's missing. Angle. We call it blade angle. You didn't tell me how much opening it is. Okay? Because this angle will be less than 90 degrees. Right? The angle can be very small, can be very big, but cannot it has to be less 90 degrees, because if it is 90 degrees, then you'll become annular. All four are connected, right? So it probably even tell you even more practical. You need to be less than 85. So the angle, the plate angle, is what need to be defined in this illumination, right? You have then this illumination will be completely defined, right? You have in, out, and also you have an angle. It's always like this type of shape. If you have a smaller sigma in, that means it is go inside. If it is a large sigma out, then it will go outside, right? So if the sigma in is 0, that means that it go all the way, become like this, right? So usually they will have some limit in the sigma in. They won't let you go all the way to 0. Otherwise, it does not make sense. You become conventional. So that's why it has 3 parameters: sigma in, sigma out. Sigma out probably will less than 0.96 also, right? It cannot be larger than 1. And also, sigma out cannot be small or equal to sigma in, right? It probably, it won't let you do like 0.96, 0.95 either, right? Because it's so small, right? It's very difficult to do, right? So this is some like a detail. I mean, on the math, you can do anything. You can do almost anything, right? As long as it is logical. But in practice, it cannot do that. Okay, so that's just something that to kind of share with you guys. Okay, yeah. Or even on simulation, I have to check, but they will have some limit. They won't let you do it. And in practice, suppose this is a lens, they will not let you do very small, because in the lens you will have a so-called lens heating. You will heat up this point. A lot of energy go to all these just a single point and heat it up, and then you will cause issue when you do the imaging. So all this is only good on the math, on the paper, but cannot be done in reality, in practice. Okay, so let's continue. C quad is this one, okay? This is C quad. Okay? Compared to this, rotate 90 degrees. Okay? And then final is dipole. Dipole on ASML tool, they don't do it this way. Okay? Basically, it is just a subset of the C quad. Dipole at ASML tool, you go like this. Okay, so again, you will need to give sigma, what is sigma in, sigma out, and plate angle. And also, at the dipole, you probably need to define what is this vertical pair, or it is horizontal pair. Okay, dipole only have one pair, so either this pair or that pair. Okay, it's not C quad. So you need to tell it's a X dipole or Y dipole. Okay, so at ASML tool, Of course, you can do more than these, but majority what we use are these illumination. We don't use this called this way or this way. This is not what we use, and we don't use kind of like circular quadrupole. Yeah, because as you can see, if we use this way, it's very difficult to put the parameter. With these, you can easily sigma in and out with parameter. For this one, we have tried. Basically, I think one thing is that it's probably very difficult to do it on DOE. But on the other hand, you have only two parameters. One is what is this distance, right? The center of the circle, what is from the center of the lens, and the other is the diameter. You have only two things. One is the distance from the center, right? You can have here very close to the edge, and the other you can have the diameter large or small. But for this one, you have three parameters you can choose, right? Sigma in, sigma out, and blanking. Okay. So in practice, at SNO2, you use these. You don't use these. Okay. But at the packaging tool, if they use the SNO, they probably also follow these. Any question? Okay. So now we want to explain what's the benefit of using OAI? Why do we need OAI? Yeah. Except conventional illumination, everything else is OAI, off-axis illumination. So we use annular illumination as an example. Okay? So if we have conventional illumination and we have very high resolution, so if we are lucky, it basically is within resolution limit, then we'll be able to collect 0, +1, and -1, right? And we'll form image, right? But then if we kind of make the resolution higher, then the angle becomes larger and larger. Eventually, this angle will become so large, then we won't collect the plus and minus one, right? That's what we call resolution limit. And at this point, if we use off-axis illumination, and you can see we're going through an angle, right? And you can see the angle here is like this much. We're basically from the center to the edge. But if we're going from one end to the other end, two beam interference, then even it is outside here that we cannot form image, we still can form image here because the 0 will go to one end, the other +1 will go to this end. We have much larger distance at the same angle, right? We can almost, like intuitively, you will see that you can almost get like 2 times as much angle to be able to form 2 beam interference. So that's the reason we need to use OAI, because OAI does have a higher resolution. Okay, so that's why I think in the previous slides, not this lecture, previous lecture, we tell you that OAI will improve the K1. Because conventional here, the K1 cannot reach 0.25. OAI will be able to do that. And this is just this one, but like for the dipole, we kind of improve the contrast because we only really focus on only like a 2 point here without the interference of other area. And but just from this figure, we tell you that with the same angle, conventional illumination will not be able to collect the +1, but with the same angle, with the OAI, we will be able to collect the +1, and then at least this 0 and 1, we have 2 beam interference to form image here, and that's a foundation, and that's a reason we're using OAI for high resolution imaging. And so this is an example that we are doing. And so the blue one is a 0th order, and purple one is plus and minus 1. And so if we use annular illumination NA 0.63, sigma 0.87, sigma out 0.87, 0.57. And so this is a CD, right? So CD is half pitch, and we show you at the objective lens. And this is the overlap of the first order and the pupil. Pupil basically is the objective lens. And you can see that the 75 is in there. And then if we decrease the CD, basically decrease the pitch, right? The pitch is double the CD, and we start to see the first order and +1 and -1 order. It will start to increase the angle, and it will move out of the pupil. So now it's only 35%. It's still collected by the objective lens. And when you go down to 90 nanometer, only here, very small portion, only 13% is there. 80, then 0. Okay, even OAI is 0. Okay, if you remember, think about the point source. If it is a coherent, 100% coherent, over here, we probably only can image 150, right? Anything go below 150, it is outside the pupil. But because we're using sigma, not 0, partial coherent, we can still do the imaging, right? And here, you can see that if we doing the point source, it is outside pupil, no imaging if it is coherent light. But with even with OAI, annual illumination, then the plus and minus 1 just move out of the pupil. So no overlap. So it means at 80s, at annual illumination, no imaging. So this is a comparison between annular illumination and dipole. Okay, so dipole, you can see this is 0th order. This is +1 order, as I mentioned, right? We go to an angle, so we are collecting only 0th order and +1. Okay, so +1 here is a lot of them still within the pupil. So 100% and here it go down to have only 50%, and then go out gradually. You miss, right? only this part so it missed. So the resolution also right end here cannot do the imaging. But image contrast, as you can see, here is even better than here, right? So dipole has much image contrast than annular. In the sense, both are OAI, but this figure tell you why we like dipole better than annular, because we kind of have much more imaging inside the pupil. Okay. Question? But dipole coming at a price. What is the price? This, we call it this X dipole. Okay, as I mentioned, it's X dipole because all the illumination here the pair is X direction. What does it mean? It means this one is only good for this direction. X dipole only good for vertical lines. This is X dipole. And so if we want to do the horizontal lines, this need to use a Y dipole. And for example, if you have a mask that has this kind of pattern, it will not work because X dipole, you will have problem with this area. Y dipole, you will have this area problem. So if you have 2D imaging, you need to use quasar or C-quad. Dipole only good for one direction. Okay. So it's a trade-off. You get very good image contrast, but on the other hand, it is only good for one direction. Okay. When you have a crank, we call it crank this way, you will have problem. Okay, so this is just some imaging, some like term explanation. OAI is an oblique illumination, so it will cause the shift in the position in the diffraction pattern. Okay, and partial coherence, as I mentioned, like we have the sigma in and out that define the range of the angle illumination, and coherent means is a 0 point, like a sigma is 0, is like a point source. And the incoherent is kind of the larger from 0 to 90 degree. But partial coherent is at the angle range. And so the resolution for line space, it is a small feature and have a two diffraction order. In this case, usually it's 0 and +1. So we need to have a proper tilt so that we can collect and to have a two beam interference. Coherent, as if we use like a conventional illumination, is a three beam interference. But if it is OAI, oblique illumination is the two-beam imaging. So each point in the source would form an image there, and they would kind of changing the phase with each other. So it is called coherence. And final image is a superposition of all these interference. And then we use a simulator to do this one. So unfortunately, this year we don't have time to do simulation practice. But this year you guys are lucky. We do some hands-on experiment in the common lab. So that's a difference. Okay. So what's the next step? When we do a step further, at SML about 10 years ago, they have an illuminator called flex ray. Okay, so if we call it a quasar, SML quasar illumination. As we see, this is a sigma in, sigma out, the blade angle. Okay, and this is a mask. So we have some dense area and some, like as you see, some isolated area. And so this green area is what they put the, we call it SREF, like a sub-resolution assist feature. And they have a 5%, at 5% of EL, the depth of focus is only 74. So look like these. And then they have a simulator called SMO. So in this, they use SMO stand for source mask optimization. Okay, so in this case, basically they only do SO. SO is a source optimization. Okay? So in this case, except for this one, they break it down. They look at all these small features and find out what is the best for them. For example, maybe they need to have this area to have a best window. And for this one, they may have this one for the best window. So they add all these illumination together, and they call it free-form illumination. So it is it's so-called free-form because you no longer only have sigma in, out, and blade angle. You put in your feature, which is a mask. Okay? And if you don't do your mask, if you don't change your mask, you only do source optimization. If you can also change your mask, then it will be source mask optimization, SMO. And then they'll tell you how you modify your mask and also how you optimize your source. Illumination in SMO's term is called source. So it's a SMO, source mask co-optimization. So they will change your source and then change your mask. And then with a new mask, they go back to change your source and then change your mask. And then eventually they gave you the final illumination and final mask. And you can see that from 74 EOF, now they improve almost 50%, go to 110, at the same 5% EL. So especially for 193 immersion, that's very expensive but very efficient way to do it. Yeah, as I told many of my students, they need big enough depth of focus to be able to do manufacturing. But the ASML tool right now, they allow you to do this type of illumination. Come with a price. Flex ray usually is an option, and then it will cost like if I remember, like a $2 to $3 million US to have that option in the tool. Okay. Before they have a flex ray, yeah, I need to tell you what is a so-called DOE. Okay, what is DOE? Let's go back here first. I mean, beforehand, before they have a flex ray, what they do is actually at the pupil, you have this mask design, and you do the simulation that tell you that this is the best illumination. What do? They at the pupil, they put a DOE. So at the DOE, they kind of drill a hole here. They drill a hole. So the light can only go through that hole. So you can see a lot of light was wasted. It was blocked. So no light goes through here. So you can see that here maybe only 5% of the light goes through those holes. Right? Only, and also the intensity is even because you drill a hole is a blade. So the hole goes through there, and it's not even the same as a simulation. So it is wasted. So that's a step one. The alpha tool doing that is a kind of the metal plate that has light goes through those areas. And second phase, they do a DOE. Okay. They call it diffractive optical element. Okay. Because previously it's lost, right? You drill a hole, only light goes through that. Second, they do a DOE and have the laser go through that and produce the light as you want. Okay? Now they can do the simulation, get the DOE, and get whatever illumination you want without loss. It's a lossless. Okay? So DOE basically is have this optical element and then produce any of the illumination you want without loss. Yeah, everything come out. The light will go through here as you want, and you are not wasting all the light coming between all these images. So they can have a uniform. So this you can see that as a conventional illumination. You can come out here as for example, dipole or quasar without loss. That's a concept. Okay? And so we're moving from blade to DOE. And the most modern one is flex ray illuminator. Because think about it, every time you have a new mass design, you will need a new DOE. And a DOE is not cheap either. DOE, as I remember, is not $2 to $3 million, but one DOE could be like $100,000 US, just one. And if you change design, you need a new DOE. If you have new design, you need to change DOE. So it all adds up, and you need to take it out, put it back in, and tool it down. And if you have a flex ray, you can just change within minutes. So it's much easier. And basically, they just use a mirror so that you will have that kind of illuminator in this type of So here I want to give you rule of thumb for illumination, because in the future, if you work as a photo engineer, lithography engineer, okay, so and especially in packaging, you're probably not going to use a flex ray, but if you're using a kind of cutting edge, you might need flex ray to do that. Most commonly used is a conventional annular quasar C-quark dipole, as I covered previously. For the center conventional area, low sigma is for low frequency, but basically low frequency means low resolution. Edge, high sigma, high resolution. Okay, so the example is dipole, right? But the dipole, as I mentioned, if it is a vertical pair, Y dipole is for horizontal line. For horizontal pair is for vertical line. And if you have crank, then you need to forget this. Go back to quasar or C-quark. Okay? And also you need to consider common process window. And also, if you have a contact hole, a lot of time you need to think about, do you need center? Because a contact hole printing, a lot of time you have low frequency area you need to consider. Okay? So a lot of time the contact hole, you might need to use a conventional, or if you have the luxury of getting that, then you use, for example, just an example. Use a quasar and then put somewhere in the middle. Conventional plus quasar. Use this one to cover dense, and use this one to cover iso. Isolated area needs center. Conventional dense area need to have a high sigma. So rule of thumb, this one to cover edge. If you have contact hole edge, you need somewhere in the middle, low sigma in, and high sigma in to cover high resolution area. So and for just kind of the last couple of minutes of the hour, a lot of time we plot this to, besides this oval shape to show process window, we have this to show. So that means when you have a zero depth of focus, what is EL you have, right? And here tell you when you have 0.3 depth of focus, you still have maybe around 7% EL. Okay? 7% EL when you have this one. And after that, you have no depth of focus, basically. That's what you have. And also, it's a term, we call it image log slope. Image log slope is a ILS. And if we normalize with the CD, it's an NILS. So basically, it's a where has a largest slope at the image edge. Okay, so image log slope tell you if you have a flat, that means that your slope is 0. But if you have a very height, almost 90 degrees, then you have a very good image contrast, the log slope. And here tell you several things. We just talk about image log slope. Usually the higher means a higher image contrast. So when you have 6, it's larger than 3, so higher image contrast. And as you can see, we will have 0.7. Higher NA usually have a higher image contrast and than low NA. But sometimes at the end, we will have a defocus issue. As I mentioned, high NA have a smaller depth of focus. So when you have a higher defocus, high NA actually is not good. So this is 0 means this is the best focus. At the best focus, high NA has a much image contrast. But as you see, if you go down to 0.4, then lower NA actually have a higher image contrast. So that's a simulation tell you. When it is outside the focus, high NA actually decrease much faster. Last slide for today. Okay, so illumination versus contrast. Okay, so we compare conventional, annular, quasar, and dipole. And as you see, when the resolution is low, means the CD is large, then conventional, actually, the neos is even higher than dipole, right? And at the end, you will see that the annular is this one. Then the quasar is this one. Dipole is this one. So at the very end, you will see that dipole is over here is better than annular, better than conventional, better than quasar. But over here, you'll see dipole and quasar is about the same image contrast. And then better than, if it is here, both are about the same. Okay? But over here is what we usually see. The image contrast is dipole best, and then quasar second, annular third, and conventional the last one. So when we always say that dipole is the best choice for illumination, it's not always true. It depends on the resolution you want. Okay, so this one actually tells you why. Well, at low resolution, you don't necessarily need to go to dipole, right? Over here, at very high resolution, of course, you go to dipole. And over here, you may as well go to quasar, right? So it is all trade-off you need to find out what is the best illumination for your feature, the crystal feature. Okay? So that's what this figure tries to tell you. Okay, so that's what I want to cover today. And later, let's have 我们休息15分钟，然后如果有你的考卷有问题呢，我们现在就拿来问我一下，然后我看有没有加分的空间。那不要每个人都来跟我要分数，然后我们11:20再上课，然后就是用中文来解释一下。